Well, good afternoon, good morning, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinar. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. As always, we have a great webinar on tap, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the presentation, you will have the opportunity to access it later on. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during today's presentation you have a question for our speaker, please don't wait, don't hesitate, just use your GoToWebinar control panel and submit your questions, and we'll try to get to as many as we can near the end of today's webinar. All right, with that, let's go ahead and kick off today's webinar, which is getting stakeholder buy-in for chaos engineering, or chaos engineering buy-in. Our speaker today is Mikołaj Pawlikowski, who is a senior software engineer, project lead at Bloomberg. Mikołaj, thank you so much for taking the time today and speaking with us. Appreciate it.
Happy to be here. Thanks for having me.
Erxcellent. Well, I know you have a great presentation on tap, so I'm going to put myself on mute and let you get right to it.
Well, thank you for that. Yeah. Welcome everybody. Like you just said, I work at Bloomberg. I'm a software engineer, and I'm very excited about chaos engineering. And the presentation today that I prepared is on probably what's the biggest roadblock in adopting chaos engineering. It's not necessarily a technical thing. It's getting the buy-in. So what I'm going to try to achieve in the next half an hour or so is to kind of give you tools and give you everything you need to be prepared, and the questions that you might be asked when you want to share, the wonderful fruits of chaos engineering that you can achieve with that. So let's start with a quick plan of what I'm going to cover. So I'm going to start by defining chaos engineering again and defining what it's actually not, just to make sure that we're all on the same page. And then I'm going to go through like the typical scenarios, typical kind of thing that you're going to see if you, convert to chaos engineering. And then you have to actually get the buy-in so that it's on the roadmap. So we're going to go through the typical questions. And at the end, I'm going to also encourage you to go and check out my book. It's called Chaos Engineering, Crash Test Your Applications for now. It's at Manning, and it's actually available online. You can go and check all the chapters available right now and tell me, what is wrong and what I should change. It's a nice interactive kind of thing. Right. So let's start with the big question: what is chaos engineering? If you you've probably seen the definition that is on principles of chaos engineering.org, but it's really a simple and kind of broad definition. It's all the experimenting that you can do to verify hypotheses about system behavior in the presence of failure, right? So a few keywords here is the experimenting. This is a domain when we try to, be as scientific as possible about that. I'm going to talk about in a minute, there is the randomness that, we can leverage to detect things, but it's really important to be, very rigorous and scientific about our experiments to be able to prove or, disprove hypotheses. And then the hypothesis about system behavior can be anything really. It depends where you're coming from, but the goal is to just increase that confidence that you build through these experiments in your system behaving the way that you think it should be behaving in presence of failure. All right. It's equally important to kind of understand what chaos engineering is not. And it's definitely not just randomly crashing things in production. If you put it in Google, you're likely going to, land on one of those kind of catchy headlines about, breaking things in production. And there is some merit to that. We'll also discuss that in a bit, but it's definitely not all that there is to chaos engineering. The randomness, the chaos monkeys, the kind of fuzzing type of thing that you can do, it's definitely useful, but it's not chaos engineering. Chaos engineering is the experiments, the designing, running, implementing, running, and analyzing of experiments to verify the hypothesis. Okay, so let's say that I'm kind of making an assumption here that the audience here probably has heard of chaos engineering before, and the one thing that you're going to notice is that people typically, halfway through a presentation, start thinking, okay, so this is really all cool, but it kind of sounds a little bit, out there, a little bit risky, a little bit, unorthodox and controversial. And the conversation that you're going to have always kind of ends up with some variant of a conversation about the value of adding that. And that value is it's a ratio between the risk and reward, or otherwise the return on investment that you do. And this is very important to get right, because if we want to for chaos engineering to become widespread, we're going to need to have good answers for that. And this is one of the first ones that are going to be asked, right? So let's talk a little bit about the risk and the reward, right? With chaos engineering, typically your reward is that you found some problem. And depending on your situation, you might be more or less inclined to find these problems, right? If if you run something that is very, very critical, you might be a bit worried that you wouldn't potentially trigger some kind of error if you didn't go and do it on purpose with a chaos experiment. Right. On the other side of the spectrum, there is a lot of situations where finding these problems as quickly as possible, whatever they are, as quickly as possible, is cheaper, easier to fix, and beneficial. So you're going to find yourself somewhere on that spectrum, depending on what domain you work in, what kind of company culture you experience, what kind of team you are on, and you're going to be to have the kind of task to go and try to somehow put a number to that. And that might be easier or more difficult depending on your role and depending on all these factors. For example, if you are on a SRE kind of team and you want to, work with some kind of SLO, let's say that, for example, you have some kind of availability goal and you want to hit your nines, and this is kind of what you're going to be working back from to try to establish that, put that number to that reward. For instance, if we don't satisfy that SLO, we're going to have a penalty. Or, on the other hand, if we satisfy that enough of the time, we're going to get some kind of reward. So sometimes it's easier, sometimes it's much harder to put a number to it because it's kind of more in the air. So if that's the case, you can also try to approach it from the other side, from the risk perspective. What is a bigger risk for you? Is it that you will find potentially a new bug that you didn't think of, and you're going to have to fix it, and you might disturb some portion of your users? We'll get back to that talking about blast radius. But is that worse for you, or is it worse for you to not find that bug and then have it run for a long, long time potentially, and then trigger at the worst moment, right? Again, if you are the one who gets paged during the night, you probably want to minimize the amount of paging, the number of times you get called. So you might, lean towards detecting it as quickly as possible. When everybody's in the office, where no one, needs to wake up and log in, and it's cheaper and it's faster. So this kind of risk versus reward situation is going to depend vastly on where you are, but you need to be aware that this is kind of like the basic question of why we are doing that to begin with, right? There's also the fact that as human beings, we tend to be really, really terrible at estimating this kind of risks. We have this evolutionary mechanisms that kind of push us towards or away from risks, and we have really hard time, doing the kind of maths. But the maths is not that difficult most of the time. Let's say that, to just give you an example, let's say that you are concerned about your application going down, or it runs on some kind of server, right? At the end of the day, there's some kind of hardware somewhere that runs it. Let's say that you are running good quality servers and they only crash on average once every 10 years, right? So if you say that the average time to failure is 10 years for your imaginary wonderful hardware, that means that if you have 10 boxes, they're going to crash on average, if it was a uniform distribution, once a year, right? And then if you increase that scale, and you have a few thousand of them, very quickly you're going to see, even if this like very basic napkin kind of math, that it's not a question of if, it's a question of when. If you have a laptop, you buy it and you run it for 5 years and it never broke on you, it might give you an impression that it just runs forever and nothing happens to that, right? But if you aggregated all of the laptops, of people in your city, you would quickly see that the problems are just something that happens all the time. And it's very important, and it's part of kind of like the value that the chaos engineering mindset can bring you, that you think about it this way, that you think about the fact that it's not an if, it's a question of when. And with some very basic calculation, you can give examples that speak to people who make decisions and people who, have to okay your chaos engineering kind of thing. So typically with chaos engineering, it's much easier to break something than it is to find a problem in different ways. So typically you're going to be able to have a pretty good return on investment, because by setting this simple experiments, you can verify, you can quickly find issues. The problem obviously is, the other side is that if your experiment doesn't detect anything, it doesn't necessarily mean that there is nothing to be detected. That's always, a thing. Yeah. So risk and rewards and the return on the investment are going to be the first thing that you need to think about when you're trying to get a buy-in from whoever it is that your stakeholders are. Another thing that typically comes up very often, and it's probably due to some of the slogans I mentioned earlier on the internet, is that a lot of people think that chaos engineering only is chaos engineering when you do it in production. It kind of doesn't count if you don't do it in production. And the truth is that you can derive a lot of value from the stages before that. Oops, forgot to change the slide. You can derive a lot of value from doing experiments, on the previous stages, whether that's your dev, some kind of staging, or whatever, your deployment model is. Chaos engineering, there's no really a reason to not apply it to all the other stages. There is an argument that goes basically like this, that if you really think about that, all of the testing that we do, all of your unit tests and all of your integration tests and all the other things that you can do before your code reaches production, they never, by definition, can 100% test your code, because, in real life, the environment is going to be slightly different. The user usage patterns are going to be different. The configuration is going to be different. Probably, some kind of hardware configuration will be different. There will be small things that by definition will always prevent you from testing it 100%, even if you have your 100% test coverage, and that's another different story. But that doesn't necessarily mean that you should be doing chaos engineering exclusively in production. That's probably that's just the exact same rules that apply to good practices for deploying software. They apply exactly the same way to chaos engineering. So yes, you can, if it makes sense for you, do chaos engineering production, and that's probably one of the most controversial parts of it. But it doesn't mean at all that you shouldn't be doing that in the previous stages. Just like you wouldn't just push things directly to production when you're deploying them. Right? Another thing that's kind of connected to that is the idea of a blast radius. It sounds a little bit dramatic, but it's basically the set of things that can be affected by the change that you make. If you deploy something in a new piece of software, a new version of your software, you want to control what the blast radius is. You want to control what the number of things that can be affected by that. Sometimes it's easier, sometimes it's a bit harder. There are things that you can do to prevent the blast radius from being too big, whether it's a percentage of traffic or users or deploys that get the new version. The typical, all the good rules of deploying software apply exactly the same way here to the blast radius. And blast radius is something that you really need to think about, and this is going to be a very good argument when you're trying to introduce chaos engineering in your team or in your firm for the first time, because this is like a very solid way of saying, okay, yes, so technically we are introducing this failure here, and we are implementing this experiment, and it can go wrong. It can go in an unexpected way. And yes, if we weren't doing that, probably it wouldn't be triggered at this stage if there's any problem. But by setting, a means of prevention of this going too much sideways, by limiting the blast radius, you can convince these people. This is something that they understand. They understand. They do it for any other software for every deployment of that they do. So you have a common language. So this is another thing that you should think about, and this is something that you need to be prepared to discuss when you're trying to get the buy-in. Another thing is that one of the things that you're likely to hear is that, okay, yeah, so that all makes sense, but come on, we're not Netflix. We don't have the scale. We're not Google here. Why would we be doing things like that? And this is another false perception of what chaos engineering can do for you. It's true that the entire thing was invented at Netflix, and one of the first things they did was the Chaos Monkey, and that kind of shaped the perception of what can be achieved with this. But it doesn't necessarily mean that you have to have the scale of Netflix. In my book, I'm going to give you a link at the end, and hopefully you can check it out. I'm trying to show that all of the things, all of the systems, whether they are a single process running somewhere, all the way up to massive microservices deployments running on Kubernetes, all of the systems can benefit from the same methodology and the same, similar tools and the same mindset that is so important in chaos engineering. That for example, one of the things that I'm showing in the book are about taking a legacy binary that is precompiled and it's written in some kind of arcane and weird way, and you don't have access to the source code, and you want to understand, you might become responsible for that. You get a promotion, and boom, you get that new piece of software that you are now responsible for making sure that it runs well. So what do you do? Well, one of the things that you can do is just apply chaos engineering to that and see what happens, how it behaves when it can't do things, whether it's network oriented, and in that case, we have, an entire assembly of tools that you can use for network slowness and connectivity drops and stuff like that, all the way to the most basic things, like, for example, taking that process and preventing it from writing to disk, for instance, and seeing how it actually behaves, introducing that failure in a very simple way and verifying experimentally that your assumptions about what it should be doing are correct, that they're true, right? That the retries that's supposed to have, that the logic, the fallback logic, it's actually working the way that you want it to work, and that the interactions with the other systems, that whatever they might be, are also happening the way that you expect them to. So it's not really the case that chaos engineering can only be applied to large systems. Sure, if you have a big complex system and you start introducing the failure, there's a lot of spectrum of things that can happen. There's a lot of things that can cascade, that they can cause one another to behave differently. And experimenting on this bigger kind of distributed larger systems is definitely an interesting topic, but you don't have to have a system like that to get value out of chaos engineering. And once again, going to like the return on investment, it's very easy. Like the tools have been there for a long time, and better tools are being written and they're being added all the time. And there's really not a good excuse not to do that. You can generate so much value with a few lines of code or even script. Um, so yeah, systems large and small, they are all equally susceptible to chaos engineering, and they can all provide you value by doing simple things with them. All right. The next one I have on the list is kind of, oldie but goldie kind of thing, and that you might not be in a kind of environment that has this very clearly defined mandate for stability related work. If you are calling yourself SRE or DevOps or something like that, you probably have a very good idea of how much time you are supposed to be spending on the stability versus the features. But this is, kind of like never really dies. It always somehow comes back up that, okay, so this is all cool, but we need features. It's working, we're not seeing problems, and it's sometimes a little hard to argue with, because well, yeah, you're not seeing any issues, but that doesn't necessarily mean that that they're not there. Doesn't necessarily mean that when there's some kind of underlying failure that happens rarely, it's not going to go horribly wrong, right? So with chaos engineering, we always end up talking about this stability effort and features. And good arguments for that are that this kind of experiments typically don't take too long to prepare. With the ready, to use tools, it's usually fairly quick to set them up. Most of the actual work is in understanding where and how to set them up, and then understand the results and make sure that they're scientifically significant, that we we're not misrepresenting the data or misunderstanding the findings. But Yeah, but the experiments themselves typically are pretty cheap to do. So, we can kind of try to respond to the stability versus features thing with the return on investment. And from my experience, once you find something with an experiment like that, it goes much more smoothly afterwards because there's this mutual understanding now that that was actually worth your time. So this is not necessarily, just for the case engineering, but it's definitely something that, when you're trying to get that buy-in, is going to show up, and you need to be able to respond to that with good arguments. Next thing I wanted to bring up is that chaos engineering applies to pretty much any system, and I was arguing just a minute ago that it applies to small and large chaos engineering software systems, but it doesn't stop there. If you think about that, every team is a distributed system. Every person on the team is an independent computer, with a CPU, trying to understand what needs to be done, taking actions and communicating. And there are always miscommunications. And the bigger the team, the more susceptible it is to all the things that we experience with computer systems, like bottlenecks. Imagine a situation where there is some kind of legacy system that is owned by the team, and there's only one or two people who knows really who know how that thing works, right? So what does that mean? That means that that person is a single point of failure and potentially a bottleneck too. That means that if that person is on a holiday, well, we're going to have a problem if this thing blows up, right? If anything goes wrong, are we going to call them? Can we wait? When are they back from the holiday? And this is the kind of thing that we really, really don't want to be doing, right? We don't want to be calling people on holidays, except that with this clear defined example, it's kind of obvious. Okay, we just said there's one person or maybe two who know this, and it's easy to identify. And maybe when before the person leaves on a holiday, they're going to hand off some data or some documentation or whatnot to someone else to kind of keep an eye on that. But most of the time, life doesn't really work that way in this clearly defined ways when we know things. The knowledge graph is, constantly shifting. Um, it's never settled, so it's difficult to see some of these things, and it's difficult to see, who the real bottleneck is, and sometimes our assumptions about things are clearly wrong, and this is a very, very interesting aspect of chaos engineering, and you can do things to detect this and make them better. You do experiments. Typically, when we experiment on teams, people don't necessarily enjoy this being called experiments. So people call them games or things like that. But the same way that you can set up a case experiment to detect a bottleneck in your system by, for example, taking down each of these elements one by one and checking how the throughput of the system as a whole is actually changing, you can do exactly the same thing for your teams. You can take one person off, or you can ask them not to talk about a particular subject, or you can ask them to work on something completely else, completely different, and you will see the bottlenecks popping up immediately. There is a really good presentation from the first Chaos Conf that inspired me to add a chapter on the chaos engineering for people into my book. That's chapter 13, unless we change the numbers again. Um, but if you want to look kind of deeper into that, there are different games that can be done. There are games that rely on network slowness. meaning that, for example, you ask a person to be slow about a particular subject and see what happens, see how that bottlenecks. Or even you can go a step further and you can see that if you ask a person to give false information, does the system self-correct itself? Do the people actually find out that the information that they were given was wrong? They were given the wrong information on purpose, and how long does it take? Do you need to interfere? Do you need to actually go and check and say, okay, now this is clearly wrong. You didn't, do a double take on that. You just took that value at the face value. These are all great games. They can help you improve the efficiency of the team. They can help you find those weak spots, and they don't cost much, which is also great. But the reason why I'm bringing them here really is because of the fact that they are also an exceptionally good way of generating the buy-in from your stakeholders, because this is something that everybody understands. If you do an experiment like that and you detect a slowness or a bottleneck, a single point of failure that is non-obvious, through an experiment like that, this typically works really well to kind of illustrate the value of that, and then you have an easier time to kind of try to sell it next time that you want to do chaos engineering in your new team or in your new firm. So it's kind of like non-obvious and very interesting. And there's more details that you can find in my book. I also encourage you to find on YouTube the presentation from ChaosConf 2 years ago. I'm sorry, I'm forgetting the name of the person now. I feel horrible for that. But it's really great. You'll be able to find it. All right. So these are the main kind of pain points that I've identified over the last few years, being kind of deep into this case engineering thing, the hoops that you typically have to jump through and explain to different people, and then what we're doing actually makes sense. So my goal here really was to just kind of give you some preparation for that, so that you can go to your new teams and your new companies and spread the good word about the chaos engineering. And before I conclude, I wanted to also invite you to go and check out my book. It's in this thing called MEEP, Mining Early Access Program, I think. Which means that you can actually go and check some of the content of the book for free, and you can go and put comments. So I got some really good feedback from people, and it would be amazing if you also wanted to go to mining.com/book/chaos-engineering. I think we're going to put some kind of link down there in the description, and take a look. The book is trying to kind of go across the different stacks and different environments that you are likely to encounter when you're doing chaos engineering. And it's kind of trying to build your knowledge bottom up. So the book is really focused a lot on Linux because of the fact that it's kind of everywhere. And a lot of the systems that you're going to run on Linux. So it's trying to kind of build up all the knowledge that you need to implement this different chaos engineering experiments at the different levels from the ground up. So it's not like, oh, here's the latest, coolest tool, although we do cover some of that too. It really tries to make sure that you build this kind of ground up knowledge, including the tools, including the underlying technologies, that you understand how it works, and that you can implement this experiment with the existing tools and don't have to rely on any particular vendor for that. So it goes from like basic things into in terms of visibility and observability on Linux, because that's part of the thing. It's part of what chaos engineering is. I mentioned earlier that we need to be scientific. In order to be scientific, we need to be able to use metrics that are objectively quantifiable, and we can observe them. So that's what we typically call observability in the context of chaos engineering. And the different tools, whether it's something as simple as Tab that shows you the CPU usage and the memory usage of the different processes on your system, all the way to pretty expert tools that let you instrument the kernel to give you the statistics that you care about. For example, to find out all the files that are being opened on the system, or to measure latencies on TCP, or to do all kinds of things with eBPF. And then once we cover that observability, we build up on the different other layers. We look into how to induce slowness on to your application. Like, it has a database, and what happens when the database slows down by a certain amount, and whether our assumptions about how the application as a whole is going to slow down are actually correct, and how to verify that, all the way through Docker, and going to like deep detail into how the Docker leverages the underlying Linux features to implement the Linux containers, and what that means from the chaos engineering's perspective, and where the weak points potentially might be. And we go into building some chaos engineering experiments on that. And and then we build up on top of that. We introduce some chaos engineering into the application itself. We introduce chaos engineering and failure into JVM by rewriting the bytecode on the fly to inject the kind of failure that we expect to modify behavior of an application without actually having to recompile it. And we finish by doing chaos engineering on Kubernetes. So both on the application running on top of Kubernetes, and then actually diving deep into how Kubernetes works under the hood. And for all of those who run their own clusters, or who just want to understand what the weak points are and try to understand what happens when things stop working and how to verify that, we dive into that, and how to apply chaos engineering to verify that your system is stable. So the goal here with the book is really to kind of just give you all the tools that you might need on your journey into the wild, applying chaos engineering to make systems more reliable. All right. And yeah, my last thing, you can also get a discount. I think we'll be having some codes, and also during the early access, you can get a discount on that. And I think that's it for me. Do we have any questions?
Yeah, I think we do have a couple minutes for question and answer period. We've gotten some questions in, but there's plenty of time. If you have a question, please go ahead and use your GoToWebinar control panel and submit it. If we can't get to your question during the webinar, please know that that we will be getting I'm sorry, Miguel will be getting a copy of all of the questions that come in. So I'm sure he'll be more than happy to follow up offline to get your question answered. But the first question here is, in production, should you be doing chaos engineering?
Yeah, that's always the first question. So I kind of touched on that before, and to kind of just sum up a little bit, you can, and there are instances where that can provide you with outstanding value. But before you get to production, like with any other deployment of any other software, you are going to want to apply the the reasonable principles and make sure that you deploy it in a way that you can roll back quickly, and that you don't do it all at once, and that you go through all of the stages that you typically go. The kind of misconception is that chaos engineering is just doing things in production, and it's part of it, but it doesn't necessarily mean that it stops at that. It can be useful, but there will be plenty of systems where that might be a problem. And if you run systems that people's lives depend on them, and if you try to run chaos engineering on something like that, if you do it badly, you might end up hurting people. So that's something that you're probably not going to do, or you're going to do in a very controlled manner. I guess the bottom line really is that you can, and sometimes it makes a lot of sense, but please just stop saying that it's not chaos engineering if you're not doing that in production. Makes sense.
All right, great. All right. Next question. When actually should you be doing chaos engineering, and when should you avoid it?
That's a good one too. My opinions might be a little bit biased, because I tend to think that you can apply chaos engineering to pretty much anything, and you can generate value with that. It kind of goes back to the previous question a little bit. There will be exceptions where it might not be acceptable to knowingly cause some kind of failure. So you're going to prefer to potentially have some kind of bug and not find it at that time, because really bad things can happen if you do. But most of the time, and most of the systems, they're going to be open to that. And if you really can't do it on the production one, really just do it on whatever staging or pre-production stage that you have in there. There isn't any language or any platform that chaos engineering is limited to. It's a mindset, and it's a methodology, so it can be applied to anything. It can generate value for you.
All right, great. I think we have time for one or two more questions. Let's see, next one. What tools can you use to implement chaos engineering?
Right. So typically, people who ask me that question, they kind of fall into two categories. They either want to know, what the latest and greatest and most powerful tool there is for it, or they actually want to know where to find this tool. So if you if you are starting with chaos engineering and you just want to kick the tires, there are some very easy to use offerings that you can go and pay someone money to get you started. But as soon as you understand what the chaos engineering really is about, it's it's kind of easy to start looking for kind of weak points of your systems. And then from there, it's just one step to designing chaos experiments for your systems yourself. So a lot of the tools that we use to implement the chaos experiments have been there forever, or for a long time. The observability tools that we use also typically have been there for a while, and there might be new, better ways now to look at them. For example, instead of looking at top, you might be looking at a nice Grafana dashboard that lets you see things over time instead of refreshing the screen in kind of like time-lapse way. But at the core of it, these are improvements that make it easier to apply the chaos engineering principles. They're not necessarily required. So that's why, in my book, like I mentioned, I'm trying to kind of build you up from all the small tools and all the underlying technologies, so they understand that, and without using anything too fancy. But obviously, for those who like the kind of high-level tools, and once you've built up this understanding, you're probably going to want to move to a higher level tool. There's a few open source options that I recommend. There is, well, obviously I'm partial to Powerful Seal. It's a tool that I'm maintaining for Kubernetes chaos engineering. So if you're in Kubernetes, whether it's for the application running on Kubernetes or whether it's for Kubernetes itself, go check out Powerful Seal. It's very customizable, and you can write different scenarios for that. Otherwise, there is also Litmus that works on Kubernetes. That's very good. And for kind of more generic all-purpose usage, there is a tool called Chaos Toolkit. And it's also open source. There is a company behind that supports it, and you can get premium offerings for that, but the core of it is open source, and it lets you in a kind of similar way to what Powerful Seal allows you to do for Kubernetes, to describe the more generic kind of experiments, including the validation, verification. So that's like the three from the top of my head that I would recommend using.
All right, great. Last question, then we'll go ahead and close out the question and answer period. Is there a place where I can go to find out more about chaos engineering?
Sure, absolutely. I am running a newsletter at chaosengineering.news that you can subscribe, and you can go and get an occasional email about that. That's one good way. Alternatively, there's also a good awesome list on GitHub, awesome chaos engineering. If you type it in Google, you'll definitely find it. It's pretty good. It tends to be up to date. It has tools. It has links to books, presentations, conferences, and stuff like that. And I highly recommend that if you want to look for that. And yeah, I think this too should keep you up to date, really.
All right. All right, great. Well, that is all the time that we have for the question and answer period, but I do want to thank everybody who did submit questions. And as I said earlier, if we did not get to your questions, I apologize, but Nikolai will be getting a copy of all of the questions that came in, and I'm sure he'll be more than happy to follow up with you offline to get your question answered. Also want to remind the audience that today's event has been recorded, so if you missed any or all of the event, you will have the opportunity to access it later on demand. Following today's webinar, we are going to send out an email that contains a link to access the webinar on demand. And the webinar is also going to be living on the devops.com website, so you can always go look for it there. Just go to devops.com/webinars, look in the on-demand section, and it should be right there waiting for you. Nikolai, thank you for a great presentation, lots of interesting stuff, and pretty much everything you need to know about chaos engineering, sort of, but amazing stuff. Thank you so much, appreciate it.
Thank you, it was a pleasure.
Thank you. Okay, great. Also want to thank the audience for joining me today. This is Charlene O'Hanlon, and I am signing off. Have a great day, everybody, and please stay safe.